So we're going to continue talking about covalent bonding, and just as a refresher, in the previous video we talked about making single bonds where you share 2 electrons. Right? We said a single covalent bond is where you share 2. A double covalent bond is where you share 4. And a triple covalent bond is when you share 6. So we looked at the diatomic elements, we looked at hydrogen, we looked at oxygen, we looked at nitrogen, we looked at the halogens, right? We looked at chlorine, bromine, and iodine. By the way, if you look on the periodic table, I should put them in a different order. If you look on the periodic table, they kind of make a 7. It goes hydrogen over to nitrogen, fluorine, and then down, and there are 7 diatomic elements. So just a little trick to remembering them. What I wanted to talk about in this video is the types of covalent bonds. Other than classifying them as single, double, or triple, types of covalent bonds based on how they share, not on how many. So how many electrons are being shared is what determines a single, double, or triple bond. But what I want to talk about is how they share the electrons. And so what I wanted to do is compare 2 different bonds. Or I guess we could compare 3. If I had a hydrogen atom sharing with a hydrogen atom, I want to compare that to a fluorine atom sharing with a fluorine atom. And then I want to lastly share between a hydrogen and a fluorine. Now I drew them out rather quickly. We did hydrogen diatomic in the previous video, and we did fluorine diatomic in the previous video. With the hydrogen fluoride, if we wanted to go through that in more detail, hydrogen has 1, it wants 1 more, and then we would have fluorine, it would have 7 and need 1 more, and so they're going to share this. I could tell you one other little trick that works rather well. If an atom needs 1 more electron, it typically makes 1 bond. If it needs 2 more electrons, it typically makes 2 bonds or a double bond. And if you need 3 electrons, you typically need 3 bonds or a triple bond, and so on. If you need 4 electrons, you need to make 4 bonds. We're going to come back to that in a little bit. So what I wanted to do is look at the types of atoms that are being shared here. So remember, what makes these electrons hold everything together is that the electrons that are being shared have 2 nuclei from atom 1 and the nuclei from atom 2. Right? And so you have the shared electrons in here, you have this attraction and you have this attraction. And so if I have 2 hydrogen nuclei and I'm one of these electrons, what's true is I'm equally attracted to both nuclei because the nuclei are the same. That's true in this case where I have fluorine and fluorine also, right? Hydrogen nucleus has a +1. Hydrogen nucleus is also a +1. But when I get over to fluorine, my nucleus is +9, and my second nucleus is +9, but I still have these electrons that are attracted. And if I'm sitting there looking at this from the electron's point of view, these electrons are as equally attracted to nucleus 1 as they are to nucleus 2 because the 2 nuclei are exactly the same. So they are equally attracted to both nuclei. Now, when I get to the situation where the atoms are different, this is 2 of the same elements, 2 atoms of the same element, 2 atoms of the same element for fluorine to fluorine. What happens when I have 2 different elements, as in hydrogen fluoride? This nucleus is +1. Fluorine's nucleus is +9. If I'm one of these 2 electrons, the question is, am I equally attracted to this +9 as I am to this +1? Now, if you don't have any physics in your background at all, you can think about this as electrical attractions due to the magnitude of charge. But I can give you a everyday kind of experience. Well, I guess not every day, but an experience you could relate to better. If you had a pile of money and in this you had $10 and you had another pile of money that had $150, and I told you you're in between them and you can have one of those piles, which pile would you be more attracted to? More people are going to go for the $150 than are going to go for the $10. The higher the magnitude, the value, the more the attraction. That is true for electrical attractions as well. So if you're this electron, what's probably true is that you are more attracted to fluorine than you are to hydrogen. Now, that's a simplistic way to look at it, because then what you would have to argue is electrons are more attracted to atoms that have higher atomic numbers than atoms with lower atomic numbers. So I'm not really telling you the whole picture with just the magnitude. When you're looking at the attractions, it's based on two factors: magnitude of the charge, and it's also based on the distance between the charges. So what happens is when you're looking at the actual attraction, if you have a electron that's here, but the nucleus is way over here compared to a nucleus that's here, this has a larger distance. So it would be a lower attraction. This one has a shorter distance, so it has a greater attraction. That's if all the charges were the same. If the charges change, then the higher the charge, the stronger the attraction. And you might have, this is true of electrical charges, it's also true of magnetic attractions. So did you ever play with magnets? And if you have a positive and negative magnet and they get close enough to one another, at some point they just snap together because the attraction becomes so great, it just happens. So when you measure this attraction, it's both the distance and the magnitude that matters. So one way to measure how well different atoms attract electrons is to use a value called electronegativities. Electronegativities measure the attraction between shared electrons and an atom, or you could say the nucleus of an atom. Electronegativities, the higher the value of electronegativity, the stronger the attraction. And the electronegativities actually follow a trend on the periodic table. And so what happens is atoms that are small with high volume, I guess high nuclear charge to volume ratios, right, that have a high magnitude but that electrons can get really close to, will have the highest electronegativities. And so what happens is as you go across the periodic table, fluorine is actually the best at attracting electrons. And if you go down here, francium is the lowest. Now, this is group 1, and this is group 17. Why didn't I put group 18 in here? Why didn't I include the noble gases? These are not found in bonding situations. It's not really true. You can find some. Xenon has been found to make bonds, but only with expanded octets, not found in that obey the octet rule. So the noble gases don't typically make bonds. For example, helium has never been found in a bond. So we're going to exclude them. Fluorines are the smallest atoms, which we're going to come to next week in lab. Francium is the largest. And so remember, it's the distance and the magnitude of the charge. So even though francium has a much greater nuclear charge, it's also very large. So the electron's not ever really going to get very close. The valence electron will not get very close to the nucleus. So as you go across, they get electronegativity increases. And as you go down, electronegativity decreases. This is an example of a periodic trend, which we're going to study in more detail coming up. So as you move across a period, they will become more electronegative, and as you move down a group, they will become less electronegative. So why does that matter? We could predict if atoms are going to share electrons evenly or not. So if I have a carbon-to-carbon bond, they're going to share the electrons evenly, because both atoms have the same electronegativity. So if you're an electron being shared, you have an equal attraction to both sides. If I look at an oxygen to carbon bond, they're going to share the electrons unevenly because oxygen and carbon have different electronegativities. Now, looking at a periodic table, it goes carbon, oxygen, nitrogen, and they're in the same period. Since oxygen is closer to fluorine, oxygen will have a higher electronegativity, and carbon will have a lower electronegativity. And so the electrons are going to be more attracted to oxygen and less attracted to carbon for this particular bond. And so we can try to distinguish between these bonds based on if they're sharing the electrons evenly or if they're sharing the electrons unevenly. And the words that we use for that is it's a polar covalent bond if they share unevenly, and it's called a nonpolar, or some people will call it a pure covalent bond if they share evenly. So you need to be able to use the periodic table and know about electronegativities in order to decide whether things are polar or nonpolar. So let's just look at another couple examples, and I want to throw another term in here as well. What if you had a bond between carbon and nitrogen? What kind of bond would that be? Well, again, it's going to go carbon, nitrogen, oxygen. Nitrogen is further over than carbon, and so this will have a higher electronegativity. This will have a lower. And so this would be considered a polar bond. Now, when they measure polar bonds, they use something called a dipole moment. Dipole moment is dependent on what we were saying before, the distance and the differential in attractions, or the difference in nuclear charges. And so polar bonds have a dipole moment that is greater than 0, and nonpolar bonds have a dipole moment equal to 0. And so we're not going to go too far into that. When you get to Chem 1A, you might see more about dipole moments, and for sure when you get to organic chemistry, we use dipole moments. But you might see somebody saying it's a polar bond, or you might see them saying it has a dipole moment. That's meaning the same thing. If it has a dipole moment greater than 0, then it is polar. What if we had a bond between oxygen and sulfur? And I asked you, what kind of bond is it? On the periodic table, sulfur is below oxygen, so oxygen would have the higher electronegativity, and sulfur would have the lower electronegativity. And so this would be a polar bond. And now I could add in one more thing. Which direction is the bond polarized? That means where are electrons more dense and not as dense? And remember, electrons are negative. So for carbon and nitrogen, nitrogen has the higher electronegativity, so the electrons are going to go more towards the nitrogen. In oxygen to sulfur, oxygen has a higher electronegativity, so the electrons are going to move more towards the oxygen. Now, if the electrons are more towards the nitrogen, then there's more negative around the nitrogen, and the carbon kind of becomes a little bit positive because it's kind of lost some of its electrons. So you can write this with the arrow and put a little plus sign at the end of the arrow. That's one way to designate it. Or you can use the symbol lowercase delta, and lowercase delta in science always means partial. So I could say that the nitrogen is partially negative and the carbon is partially positive. I wouldn't use both the deltas and the arrow. That's redundant. In oxygen to sulfur, I would say that the oxygen is partially negative and the sulfur is partially positive. So you can use one way or another to indicate the direction of the dipole moment. The arrow's pointing towards the negative side, or you use the delta negative. The negative is always towards the atom that has the higher electronegativity, or that is attracting the electrons better than the other, or more than the other atom. So what I want to do in terms of all of this is give you an overall summary of bond types. And so we're going to say type of bond, when it occurs, the difference in electronegativities, I'm going to make a little grid. So what we're saying is if the difference in electronegativities between the two atoms is 0, it's going to be a nonpolar covalent bond. Right? If there's no difference in the electronegativities, the atoms have to share the electrons evenly, and it will be nonpolar. When will this occur? When you have two atoms of the same element. Right? If you have two atoms of the same element, they have the same electronegativities, so it must be a 0 difference. Let me jump over and do something where you have a large difference. If you have a very large difference in electronegativity, and we're going to have moderate. Now, what happens if you have a really big difference in electronegativity? So let's look on the periodic table for a second and say that we have a fluorine bonded to a francium. I'm just picking those two because this one has the greatest electronegativity and this one has the lowest electronegativity. What if I mix those two atoms together? What's going to happen is that fluorine is going to have such a stronger attraction for the electron than francium that fluorine's basically going to take francium's electron. And if fluorine takes the electron, then what I'm really going to have is a fluoride ion, and I'm going to have a francium ion. And once I have ions, then I'm not going to have a covalent bond. I'm going to actually have an ionic bond. When does this happen? It happens when you have a very large difference in electronegativity. And when do we have that? This is the area of the periodic table where there's very high electronegativities, high values. And down here is when you have low values. Up here is where all the nonmetals are. And down here is where you have metals. So what happens is whenever you mix a metal, which has a low electronegativity, with a nonmetal, which typically have a very high electronegativity, you're going to get a big difference. So when you have a metal and a nonmetal, you're going to have a large difference in an ionic bond. There are a couple right in the gray area, but I'm just giving you generalities right now. When will you have a moderate difference? Well, first of all, what you need to know is, if you noticed in all my examples, all the examples of covalent, I only used one particular type of element. I only used nonmetals. And that will be true. So when you want to make covalent bonds, you're really not going to have metals involved in that. So covalent bonds are really between the nonmetals. And so when you have a moderate difference, what you're going to have is a polar covalent bond. And that's going to occur when you have two different nonmetals. And up here, you could say same element, but they'd be nonmetals. So in general, you can use these little rules to quickly decide. So if you see something that is lithium chloride and I ask you what kind of bond, lithium is a metal and chlorine is a nonmetal. And so once you see a metal and a nonmetal, you should say that this bond is ionic. If I gave you an example of chlorine to oxygen, these are two different nonmetals. And so you should answer that this is polar covalent. Now this works really well. There are a few places where there's a gray area between where do you cut this line and where do you cut that line. Different textbooks actually might have you calculate it. I don't really see any point in that. But one exception I do want you to remember to this, because it's going to become important later. Turns out that carbon and hydrogen have about the same electronegativity and they are considered nonpolar. And so I'm going to put that in two places. Whenever you see a carbon bonded to a hydrogen, if you just went by the rules written in red on our chart, you would think carbon to hydrogen should be polar, but I'm telling you, you need to just remember these are nonpolar. Turns out they have just about the same electronegativity. So they have a slight difference, but they're still considered nonpolar. So here's a scenario to kind of describe to you the different types of bonds. Say you had two kids on a playground and each kid has a ball. And so you say, okay, on the count of three, each kid's going to throw their ball to the other one. So you go 1, 2, 3, throw, 1, 2, 3, throw, 1, 2, 3, throw. So on each of those throws, a ball's going this way and a ball's going that way. And so every count of three, this ball ends up over there and this ball ends up over there. But overall, you would say that they are sharing evenly. They both have the same access to the balls. This would be kind of like a nonpolar covalent bond. My ability to write has just stopped. Nonpolar covalent bond. Now, if we do the same kind of scenario, but I go 1, 2, 3, throw, and this person throws, but this person doesn't. What's going to happen? This person would now have 2, and this person has none. They are not sharing evenly. If they left it like that, if this person had both and this person had none, and that's the end of it, they're not really even sharing. In some ways, you could say that they transferred an electron. One lost an electron and one gained an electron. When we're talking about losing and gaining electrons, what type of bond are we describing? An ionic bond. Because this one would now be negative and this one would now be positive. So those are the two extremes. Sharing evenly, nonpolar, covalent. Not really sharing at all. Somebody gained and somebody lost. Ionic. So what's this polar covalent bond? In a polar covalent bond, this person throws and this person doesn't, but then, you know, there's like that yard duty person around. So this person right now has 2 and this person has none. But then that yard duty person says, hey, 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 throw your ball. So after a while, they throw the ball. So then they go back to having 1 and they go back to having 1. Then they go 1, 2, 3, throw. They throw it. This one has 2. This one has none. And they, hey, 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 share back again. Okay, it goes back to 1 and 1. Over time, did they both have the same access? Over time, they have different access. You can think about one as being a bully, not throwing it when they were supposed to, keeping the ball even though they were supposed to throw it. Over time, this guy would have the ball more often than this one would. And so this one, if the balls were negative electrons, this one would start to become somewhat negative, and this one would become somewhat positive. This one would be partially negative. This one would be partially positive. What kind of bond am I describing? A polar covalent bond. And so the 3 types of bonds that you need to know about are nonpolar covalent, polar covalent, and ionic. And we'll come back and practice those when we get to the future videos, when we look at other molecules and molecules in more detail.